Today I will be talking about resistance and compliance of the blood vessels. This is a drawing of a single blood vessel. In this drawing, R equals tube resistance, Q represents flow rate, P1 represents the initial pressure, P2 represents the final pressure, L represents the length of the blood vessel, little r represents the radius, capital N represents the number of tubes in parallel, and little n represents the fluid viscosity. These are two very important equations for this concept. The first equation calculates the flow rate. This is calculated by multiplying the number of tubes in parallel by pi, the radius to the fourth power, and the difference between P1 and P2. This quantity is divided by 8 times the fluid viscosity and the length of the tube. It makes sense that the longer the tube or the greater the flow viscosity, the smaller the flow rate. The flow rate increases if there are more tubes in parallel, the radius increases, or the difference in pressure is greater. The second equation calculates the tube resistance. This is done by multiplying 8 by the fluid viscosity and the length of the tube, and dividing that quantity by the quantity of the number of tubes in parallel, pi, and the radius to the fourth power. This equation can be simplified to the difference of P1 and P2 divided by the flow rate. From the simplified equation, we can come to the conclusion that with the higher flow rate, there is a lower resistance. From the resistance equation, we can see that it will affect the change in pressure along with the change in the volume of the blood. This is a graphical representation of the relationship between the blood flow and arterial pressure. The gray line in the middle represents what a normal relationship would look like. The purple line represents a lower arterial pressure, which is called the sympathetic inhibition. The blue line represents a higher arterial pressure, which is called sympathetic stimulation. The point at which each graph starts is considered to be the critical closing pressure. The other part of this concept is compliance. Compliance is the ability of the blood vessel to respond to an increase in pressure by distending or swelling. Compliance can be calculated by the change in volume divided by the change in pressure. There are two types of pressure when it comes to a tube. There is internal pressure and external pressure. The compliance is calculated using the internal pressure. So the equation for compliance comes out as the change in volume divided by the difference between the final internal pressure and the initial internal pressure. Compliance is not solely dependent on the mechanical properties. It is also dependent on the length of the tube. These two tubes have different lengths, but the shorter tube has a lower compliance. This is because the vessel walls are unable to stretch as much as the long tube. The last part of this concept is elastance. Elastance is inversely related to compliance. Elastance is considered to be the stiffness of an artery. The arterial system has a much higher elastance than the venous system. For every tube, there is a volume required to inject when the tube is initially empty to just begin stretching the wall. This is considered to be the dead volume. The dead volume of the arterial system is approximately 400 milliliters. The dead volume for the venous system is approximately 2,200 milliliters. This is a graphical representation of elastance, and it shows the difference between the arterial system and the venous system. The arterial system is represented in purple. The solid line is elastance under normal conditions. The dashed line represents sympathetic inhibition, and the dotted line represents sympathetic stimulation. The venous system is represented in blue. Again, the normal situation is the solid line. The dashed line is sympathetic inhibition, and the dotted line is sympathetic stimulation. As the graph shows, the elastance of the arterial system is much greater than the elastance of the venous system.